Gases have almost identical properties. So if you have a mole of gas, you'll have the same volume, and it doesn't matter what gas it is, stuff like that. But boy, liquids and solids can certainly be a lot different. And most of the differences that you see between solids and liquids comes down to intermolecular forces. Now, again, a molecule can have intramolecular forces and intermolecular forces. The intramolecular forces are covalent, ionic, stuff like that, and they're pretty strong. It helps keep the molecule together. But intermolecular forces, which we'll abbreviate IM forces, are the forces that exist between two molecules of the same substance. So if you're ever curious, like why H2O water can be a liquid when you drink it, a solid when it's ice cube, or vapor if you heat it up on a stove. Like, it's all H2O, but they're obviously different. A piece of ice is different than steam, and steam is different than liquid water. Well, the answer as to why they're different comes down to these crazy intermolecular forces. These IM forces are like little tiny hands on the molecule that reach out to the little hands on other molecules, and they do hold on to an appreciable extent. And the strengths of these intermolecular forces, these little tiny hands, will tell you what kind of phase you have, stuff like that. Now, all of these intermolecular forces can be broken up with kinetic energy, and it's not going to take horrible amounts, too high of amounts to make this happen. So we'll talk about how kinetic energy can overcome the intermolecular forces and what that means for molecules. Those intermolecular forces are usually shown with dashed lines. So in this, both of those pictures on the right-hand side there's like a dash. So the HCl's on the top have a dash in between them. Those are the intermolecular forces. And the water molecules definitely have dashes between them. Those are also intermolecular forces. Notice how the water molecule has partial charges on them. Those are the partial polar covalent parts. Hydrogen is slightly positive, oxygen slightly negative. So the intermolecular force forms readily between the positive and the negative parts. And the same thing with HCl. The chlorine would be slightly negative, the hydrogen would be slightly positive. No problem. Here are the three main phases of matter that we're talking about in these classes: solid, liquid, and gas. And solids generally have the lowest kinetic energy, which gets the symbol E sub K. That means that the intermolecular forces, the forces between the molecules, are actually the strongest there. So solids have high intermolecular forces, but very low kinetic energy, like they don't move around. Now, liquids, on the other hand, liquids are kind of in between. They do have appreciable kinetic energy, and they do have strong intermolecular forces, but not as strong as solids. And then finally, gases have the highest kinetic energy. They're moving all around all the time. On the other hand, they have low. We even assumed they had no intermolecular forces in the gas chapter. So this is how chemists think about it. So the answer to the question that I said earlier, like why is an ice cube different from gas vapor, water vapor, which is different from liquid water? And I would say it's the intermolecular forces. A piece of ice has really strong water-water intermolecular bonds and not a lot of kinetic energy. Liquid water has some kinetic energy, but also some pretty strong intermolecular forces, so that's why it's different. And gas vapor, if you heat up water on a stove, that water vapor has the highest kinetic energy and no or very, very low intermolecular forces. Now, in reality, gases do have a little bit of IM force going on, but we will assume in Chem 222 that there's none. Okay, it just makes it a lot easier. And in advanced classes, you may have to break that assumption. But for us, that works really well. Keep that in the back of your mind. To understand intermolecular forces, you have to know the types of intermolecular forces that are possible. And how scientists differentiate the intermolecular forces is by the type of force acting in the intermolecular force. And there's actually different kinds. So what we're going to do now is we're going to look at the main types of intermolecular forces. And these intermolecular forces will affect the boiling points, melting points, vapor pressure, and all kinds of other properties of the compound we're looking at. So the 5 types of intermolecular force we're going to look at are called ion dipole, dipole-dipole, hydrogen bonding, dipole-induced dipole, and induced dipole, induced dipole. And this is actually the order of the strengths of these intermolecular forces. So we're going to see that the ion dipole force, for example, is strongest, and the last one down there, induced dipole, is weakest. Now, induced dipole is a lot of syllables and a big couple of words there. So I will abbreviate sometimes induced dipole as IDID, just to let you know. So if I say the IDID force, that's the induced dipole force. Another thing is that sometimes induced dipole has different names. Dispersion is a name that's used. Sometimes they're called London forces or van der Waals forces, but I'm going to try and keep it as induced dipole, IDID, as we go through this section.
When a gas phase sodium ion enters water, it becomes surrounded by water molecules, or hydrated. The ion-water connection results from ion dipole forces indicated by a dotted line. It is difficult to determine the number of water molecules around a hydrated ion, but 6 is a good estimate for most cations.
The ion dipole force is the first of the intermolecular forces, and it's one of the strongest forces that's out there. Now let's look at the name. Ion means something ionic. So for example, a cation or an anion, something positive or a negative, probably a metal or a nonmetal. Dipole is another word for something that's polar. All right. So in ion dipole force, you have something with a charge, something ionic, and something that's polar. And a lot of times the polar dipole part comes from water. Not all the times, but a lot of times that is. And the ion dipole force is what makes water so powerful in dissolving ionic compounds, because water has a very strong dipole. It's very, very polar, and it's able to break up the ionic positive, negative charges and things. So if you put something like sodium chloride in water, it quickly dissolves. The Na plus is surrounded by the negative sides of water. The chlorides, likewise, are surrounded by the positive sides of water. And usually the solvent way outnumbers the solute, so it's not a problem. You've got a lot of solvent molecules around each ion. This is what leads to hydrated ions in water. People actually can calculate the energy of these to better or lesser parts. But the important part for us is not about the energy. It's just that this is a strong force, because ionic bonds are stronger than covalent bonds. But good old water, with its polar side, is able to squeeze in between the cations and anions, extract them from the solid matrix, and then you end up with dissolved ions, which is pretty cool. Now, we also talked about in a previous section about compounds that are insoluble. So water's dipole is unable to squeeze in between those and dissolve them. Sometimes ionic bonds even overpower water, but there certainly are a lot of examples where water does overpower the ionic bonds, hence the importance of the ion dipole force.